Good day, ladies and gentlemen. You are all welcome to the second lecture of Buad718, which is Computer in Organization. If you can remember, in our first lecture, we presented the course content, which contains 14 items. And in that, our first lecture, we look at from item number 1 to 4. So today we are going to continue from item number 5, which is on central preparation equipment. What are these central preparation equipments? These devices that were used, let me use were used because these devices are no longer in use. Therefore, what we are doing today is also like a part of historical development of a computer. These devices are used for preparing data, for editing data, and for transferring that data into the computer according to the program written on the devices that contains the information. And among these preparation equipments, the early computers, they use devices we call punch cards. This punch card is a device that is programmed by punching holes on it in such a way that it stores an information depending on the nature of the holes punched, and it is the one that is used for transferring data into the computer. Now, this punch card is programmed by a machine that is called a key punched. What is a key punched? This key punch is a device that is used for precisely punching holes in the punch cards to make holes in different locations on the punch card so that those punches will represent the data, the information that we want to transfer into the computer for processing. The early punch cards, they were mechanical in nature, they were manual in nature in such a way that they don't have anything like an engine that drives them. No, we use our manual labor to operate them. You can see the typical diagram here. And as the technology advanced, the key punched were mechanized in such a way that they have electromechanical motors that drives them. Just like our printers today, they have motors inside. In the same way, the further advancement on the key punch made them to be electromechanical. And these punch cards devices, they were like small keyboards. As you can see here in this diagram, you can see something like a keyboard which you punch. You press for punching the cards so that you store the information you want. And they also resemble the typewriters we normally use. The key punch also, they have two segments. One segment is called hopper. This hopper is a slot where the cards which are not programmed are stored. They are kept before they are used for punching to produce stored data on them. And they also have another segment that we call a stacker. This stacker is a segment that is used for holding the cards which are already punched. Therefore, we have two segments. One is hoppers for blank cards. The other one is stackers for the punch cards. The punch cards, that is the device that is punched using the key punch, is a flexible material which is write once medium. By write once, it means once you program it by punching holes on it, it is done. You cannot change it, you cannot reprogram it. And by making those punches on it, it encodes, that is, it stores a data in it that can be interpreted when inserted into the computer. And this data that is stored, mostly it is 80 characters, and these 80 characters include the alphabets from A to Z, both small letters and the capital letters, and it is also used for storing digits, that is from 0 to 9, and some special characters like hash, like asterisk, like $, and the rest, question mark. The next thing under this central preparation equipment is a device we call a sorter. This sorter, as the name implies, it is used for sorting, that is differentiating the cards that are already punched. So we use this sorting machine to differentiate them into different categories that will make it possible for us to be ready for next processing. And the sorters were initially produced by IBM company. If you can remember, in our first lecture, we defined IBM as International Business Machine. It's a company that produces computers. This sorter has 13 pockets, that is 13 slots. And these slots are used for storing different punched cards depending on the holes punched in selected columns of the punch cards. And how does it sort it? How does it differentiate it into different categories? First of all, the sorter will examine the first column, a single column of each card that is already punched. Now, if it reads that column, it will know, okay, it belongs to slot number 1, number 2, number 3, up to number 12. And we have 12 rows. Out of these 13 we mentioned, the 12 are used for storing the cards that are already punched depending on the data in each column examined by the sorter. And the column number 13, that is one pocket, is used for storing the cards which are blank, the ones that are not punched, or for storing the ones that are rejected because of the mistakes in them, or the ones that have errors. But the other 12 out of these 13 pockets are used for storing the successfully punched cards depending on the data in the examined columns. If you look at this diagram, this is a typical diagram showing a sorter. If you can count, we have up to 13 pockets here, 12 for successfully punched cards and 1 for the ones that are blank, the ones that are rejected because of errors and other reasons. Now, among the central preparation equipment, we have what we call a card verifier. This card verifier is also another machine that is used for verifying the cards that were punched to make sure that the data stored in it, there is no error on it. And how does it do that? It does that verification by keying the same data, punching the same holes for the second time to check if it tallies with the first one. If it does, then that's all, it is accepted. If not, it will be verified for the next time and finally accepted or rejected. And this process is known as two-pass verification. The reason is because we punch it for the second time. So the cards which are successfully verified after keying for the second time, they are supplied with a notch. This notch is nothing but a sign on the right hand edge of the card to make sure that these ones are verified correctly. But if an error is encountered, what they do is this second verification should undergo the third verification to see if it is really wrong or right. Then finally, if the third attempt found that the keying was incorrect, it is now rejected, and they put a notch on the top of the card this time around to show that this card was wrongly punched. So the next item under this central preparation equipment is what we call the card data recorder. And this card data recorder is like a machine that is an advanced key punch machine. It is made using transistors. That is, it's changed from mechanical now to electronics version. And what it does is that when a card is programmed, if you pass it through the card data recorder, it will flash a light on it and it will capture the image of the punches that are on the cards. And if it found that there is an error, it can automatically erase the punch put on the card to show that this one has an error, and then it will release the card so that it will be keyed again. What we are saying here is that we know we set the punch cards, they are one-time programmable, but as the development comes, they produce cards that can be programmed more than one time, and they do that by using card verifier to check if this one is properly programmed. It will capture the image so that it will be using that image to on other cards in the same, with the same information. And it can hold up to 6 programs, meaning it can take this card number 1, number 2, up to 36, capture their images and keep in their memory, in its memory, so that it can be programming subsequent ones. Then the next thing under this central preparation equipment is what we call a program card. This program card is an advancement of the verifiers. What it is used for like automatic verification of the cards to make sure that what is punched on them is actually the information that is needed. Excuse me. This program card is also known as a drum card. The key punch, as we mentioned earlier, or the card verifier, they could now be programmed using this program card so that they can duplicate the previously programmed cards. And it is, as I said, it is an improvement on the previous versions of the key punch machines. Now, as the technology develops, they now have a transition from using punch cards as a means of imputing data into the computer, where they move to direct data entry into the computer. And this started in around 1950, where a company called Remington Rand introduced what they call a unityper. This unityper is a machine that is used for entering data directly into magnetic tape. You say magnetic tape, just remember the olden day video cassettes we have. The tape or the tape of a cassette recorder, they are all magnetic tapes. So we use this unityper to impute data into them without using the punch cards. And this was used for a computer called UNIVAC. If you can remember, we define this as Universal Numerical Integrator and Calculator. In the year 1965, an improved magnetic tape encoder was produced, which automatically replaced the key punched. And in the year 1970, or in the midst of 1970s, microprocessors were invented, and for this there is no need of using cards for imputing data into the computer. So as we were saying, gentlemen, as the microprocessors came into existence in the midst of 1970s, we have a complete transformation in such a way that we have different devices that can be used for entering the data into the computer. Things like this flash drive, like CDs, DVDs, and what have you. And this brings about a complete transition from the key punch into the modern devices we use for transferring data into the computer. So that's all about central preparation equipment, which I said it is like a historical development of the computer as well. So now we move to the next item on our content, which is item number 6, and this is introduction to binary, hexadecimal, and octal number system. If you can remember, we said the computers we use today, they are generally digital in nature. And I told you a digital computer is a computer that represents data in discrete form, and I told you it has 2 states. It is either high or low, and on or off, and these are represented by either 0 or 1. So since it has these two stages, then the binary system of a number, which is based two numbers that has two symbols, and these two symbols are what? 0 and 1, is then very significant in the computer operations, because the computer deals with only two digits, either 0 or 1, which are called bits, and at the same time it is using this binary system number because of this coincidence. However, the other number-based systems that are useful to the computer operation include the hexadecimal. This hexadecimal is expressing numbers in base 16, meaning it has element digits from 0 up to 15. If you count including the 0, they are 16. And also it uses an octal number system, which represent data in base 8 with 8 symbols counting from 0 to 7. We are going to see all of them in the subsequent sections. Now we start by the binary number system. What is a binary number system? The binary number system, as I have already said, is a system of number that has two numbers or two symbols, and these two symbols are either 0 or 1 and nothing more. Because there are two, 0 and 1, that's why we call it binary. Binary means two. Whenever you have a 0, it means there is no signal as far as computer system is concerned, and if you have a digit 1, it means there is a presence of what? Electric signal in a computer. Now, in binary number system, if you see something like this, 1 and 0, don't call it 10. Don't call it 10. It is a number that if you want to convert it into decimal, that is the normal counting system base 10 we use, you will have exactly 2. And how do we convert these two into these two bits, 1 and 0? We will see how we do that. If you want to do that conversion from binary to decimal, that's from base 2 to base 10, this is the procedure. What we use is to use powers of 2. Powers of 2. Look at the example. For instance, if I'm given this number 1001101 and it is expressed in base 2, this subscript means base 2, and we are asked to change this number into base 10, that is decimal. What we'll do is this: you take these numbers, look at them, starting from 1001101, and arrange them in that order: 1 0 0 1 1 0 1. So if you arrange them, you now come and put these 2's on them, 2 on each of them. But the last one, this last one, the 2 should have power of 0, the next one power of 1, the next one power of 2, the next one power of 3. It will continue up to the last one. The last we have here is power of 6, not because 6 is the maximum we can have, but in this case we have 7 bits. If you count them, they are 7, so starting from 0 up to 6 will give us 7. Now the next thing you will do is to take your calculator and say this 2 raised to power 6. What we mean by that is 2 times 2 times 2 times 2 up to 6 times. And if you do that, use your calculator, it will give you exactly 64. Whatever you get, here we get 64, you multiply it by 1 to give us the 64. Then if you come to the next one, 2 raised to power 5, you say 2 times 2 times 2 times 2 up to 5 to give you 32. But that 32 should be multiplied by this 0, and 0 times anything is what? 0. That's why we have 0 here. The same thing with this, if you do it, it will give you 16 times 0, it will give you 0. Here, if you say 2 raised to power 3 will give you 8 times 1, you have your 8 here. 2 raised to power 2 here will give you 4 times 1 will give you your 4 here. 2 raised to power 1 should give you 2 times 0 will give us this 0. And finally, 2 raised to power 0 is 1. We know 2 raised to, any 3 raised to power 0 is 1, and then times 1 will give us 1. Now we'll say 64 plus 8 plus 4 plus 1. If you add all of them, they will give you 87. What do we do here? What we did is that we take this number 1001101 in base 2, that's the binary, we change it into base 10, that's decimal, and it is equivalent to 87. As I said, what we do is the computer and electronics, they work with bytes. I told you each one of this is called a bit, B-I-T, bits. But most of the computers, they require a byte. And what is a byte? This byte is equal to 8 binary numbers, 8 of them. Okay, so whenever you have a set of 8 binary bits, they are called 1 byte. Each byte has encoded information that a computer is able to understand. That is, in each byte of information, of binary number, you see that it carries a certain information, and the computer can translate that information and carry out the necessary action. And whenever you have many bytes connected together, they will give you a digital data, as a large value of information. So the next thing is base 8, which is octal number system, and this simply means that we represent our numbers using 8 symbols. And what are the symbols? Look at them. We start from 0, 1, 2, 3, 4, 5, 6, and 7. If you combine all of them, you see that you have a total of 8 symbols or digits, and that is why we call it an octal base 8. One thing you should notice is that we said is base 8. You see that the largest number should be less than that base, just like in base 2. We know the numbers we have is only 0 and 1, but 1 is of course less than 2. So if we want to determine the value of a number which is in base 8, but we want to change it into base 10, what do? We follow the same procedure as we did under the binary number system. What we do is we arrange the numbers as they are given to us. Look at the number here. For instance, we are given 3623 in base 8, and we are asked to change it into base 10 number. Then I'll arrange them like this. My 3 should be here, my 6 should come here, the 2 should be here, and the 3 should come here. And on top of them, as I did on the binary, I will arrange these 8s. 8 here, 8 here, 8 here, 8 here, no matter how many they are. Then the first one I have from my right hand side, I'll put a power of 0 to it. The next one, power of 1. The next one, power of 2. The next one, power of 3. So after doing that, I'll now come and say 8 raised to power 3, which simply means 8 times 8 times 8. If you use your calculator and get the answer, whatever you have, multiply it by this 3 that is under it. And if you do that correctly, you get 1536. Then come to the next one, 8 square, which means 8 times 8. It will give you 64. If you multiply your 64 by 6, it will give you 384. You add it here. Then the next one, 8 raised to power 1, which is 8, times 2 will give you exactly 16. And then the last one, 8 raised to power 0, as we know, any 8 raised to power 0 is equal to 1. Then that one should be multiplied by 3, and this will give us 3. Now if we add this, that is 1536 plus 384 plus 16 plus 3, it will give us 1939 in base 10, that is in decimal. I hope we are together. Now let us move to the hexadecimal, which is a system of expressing values in base 16. And if we say base 16, it means we are going to use up to 16 symbols. But remember, the digits we have as far as calculation in English is concerned range from 0 to 9, which give us how many digits? 10. So in order to take care of the remaining to give us up to 16, we do this. We take our 0, 1, 2, 3 up to 9. Then the 10 is now represented by A, 11 by B, 12 by C, 13 by D, 14 by E, and 15 by F. So if you count from 0 to 9, then A, B, C, D, E, F, it will give you a total of 16 numbers. And if you notice carefully, we said the hexadecimal is base 16, but the largest number we have is F, which is 15. Of course, 15 is less than 16 by 1. So in order to do the conversion also from base 16 to base 10, we follow the same procedure as we did on the binary and octal number system. And let us take this as an example. We are given 2DB7 in our hexadecimal, that's base 16, and we are asked to change it into base 10. What we'll do is to arrange them as we did previously. Our 2 here, followed by D, followed by B, followed by 7. And on top of them, I will arrange the 16s because we are in what? Hexadecimal, which is base 16. The last one, as you know, from your right, should carry power of 0. Next one, power of 1. Next one, power of 2. And the next one, power of 3. So now, the next thing you will do is to take your calculator and see 16 raised to power 3, which means 16 times 16 times 16. Whatever you get, you multiply it by this number under it, which is 2. And if you do that correctly, it will give you 8,192. Then you come to the next one, which is 16 squared. 16 times 16. Whatever you get, you multiply it by D. And if you go back here, we said our D is equivalent to what? 13. So multiply it by 13. Doing that correctly will give you 3,328. Then you come to this, which is 60 raised to power 1. Any raised to power 1 is itself. Well, therefore, we have 16 times B. And this B stands for 11. 16 by 11 will give you 176. Then you come to the last one, which is 16 raised to power 0 as usual. Any raised to power 0 is equal to 1. And that one should be multiplied by this 7 to give us 7. Finally, we add 8192 plus 3328 plus 176 plus 7 will eventually give us 11,703 in base 10 number. That is our normal system, of counting numbers. So gentlemen, now we are going to look at the reverse process of what we have done. That is, we were given numbers in base 2, we changed them to base 10. In base 8 octal, we changed them to base 10. Hexadecimal, we changed them to base 10 also. So now we are going to see how we can change from base 10 to those other bases we have seen. And if you want to do that, this is what you will do. Whenever you are given a binary, base 10 number, you are asked to change it to binary. All you do is to continuously divide that number by 2. Whenever you make the division, if there is a reminder of 0 or 1, you keep it in each step for you to understand this. Or before that, after keeping these reminders, you arrange them from the bottom to the top, and that will give you your binary equivalent of that base 10. Example will clear any confusion. Supposing we are given these numbers: 15 base 10, 23 base 10, and 41 base 10, and we are asked to change them to base 2. So let me start with the first one, which is 15. I put it in this tabular form for simple understanding. If you look at this column, I put my original number, which is 15. And as I says, I want to change it to binary base 2, so I will now divide it by this 2. Whenever you say 15 divide by 2, you see that 2 will enter into 15 7 times, which is 14. So if you take 14 out of 15, you have a remainder of 1. We keep our remainder here. Then I'll now come and say this 7 divide by 2. If you do that, you see that 2 will enter 7 3 times. and 3 times 2 should be 6. So if you take 6 out of this, it will give you a remainder of 1. Then you come and divide this 3 by 2 again. 2 into 3 should enter 1 times, remainder 1. So you come and say this 1 also divide by 2. How many times can 2 enter 1? It cannot enter, so we put 0. But if it enters 0, definitely there is remainder of this one. I put it here. So after doing that, I will now arrange these numbers starting from this one, this one, this one, and this. That is from the bottom to the top, and that will give me my answer. And if you arrange them, you have 1, 1, 1, and another 1, all of them in base 2, which is equivalent to your 15 base 10. Second example, we have 23 base 10, and we are asked to change it to base 2. We follow the same procedure. This is my 23. If I divide it by 2, it will enter 11 times. 11 times 2, you know, is 22, right? So taking 22 out of this will left me with a remainder of 1. Then you now see 11 divided by these 2, it will enter 5 times. 5 times 2 should give you 10. Taking 10 out of this will give you a remainder of 1. Then this 5 divided by 2, it will enter 2 times. 2 times 2, which is 4, right? So we have remainder of 1. Now we'll now see how many times can 2 enter into this 2. It will enter exactly 1 time without any remainder. Therefore we put 0 as our remainder. Now finally we'll see how many times can these 2 enter into this one. It will enter 0 times, but remainder of the 1 itself. So if we want to find our final answer, as I said, we arrange from here to here, which is the first number here. We have 1, then followed by 0, followed by 1, followed by 1, followed by 1. So my 23 base 10 is equivalent to 10111 base 2. Here I made a mistake. There are supposed to be 3 ones, not 4. So the last one here, we are given 41, and we are asked to change it into base 2. The same procedure. I'll say this 41, how many times can we how many 2's can we get in 41? We'll definitely get up to 20, because 20 times 2 should give us 40. But remember, our original number is 41. If you take 20 times 2, which is 40, it will give you a remainder of 1. Then you now come and divide this 20 by 2. It will enter 10 times exactly. The remainder should be 0. Then you divide the 10 by 2. It will enter 5 times exactly. The remainder should be 0. And then you come and divide the 5 by 2. You get 2 times of 2. That's 2 times 2, which is 4. So if you take 4 out of this 5, your remainder should be 1. Then the 2 itself should now be divided by another 2, and we'll get 1. And the remainder should be 0, because 2 will enter itself exactly without any remainder. Finally, I will say this 1 divided by 2. We know it will enter 0 times, but the remainder of 1 itself. As usual, we arrange these reminders from the bottom to the top. So in this case, you see I have 1 followed by 0, 1 followed by 0, 0, and finally 1. So if I arrange them, I'll have this 1 0, 1 0 0, and 1. This is equivalent to my 41 base 10. So the next thing is, if you don't want to do the conversion of the binary number using that tabular methods we gave, there is another way of doing it. How? The procedures are the same, only that the first one we did, as you can see here, we put it in a form of table. But if you wish, you can use this method, which is also correct. How do we do that? And if you want to do that, whenever you are given a base 2 number and you are asked to change it to base 10, all you need to do is each of the bits you multiply it by 2. You multiply it by 2. After multiplying them by 2, your last 2, the most right one, you put a power of 0 to it. Then you keep on increasing, just as we did when we use the tabular method, and after that you add everything together to give you a complete result. For us to understand this, let us look at these typical examples. We are given these three numbers, this 11010 base 2, and this 110011 base 2, and finally this 100010001 base 2, and we are asked to change them to base 10. In order to do that, let me start with the first one, which is this. As you can see, the bits I have here are 1, 1, 0, 1 and 0. So I'll take this first one and multiply it by 2, put them in bracket, plus the second one multiplied by 2, close the bracket, plus the next, which is 0, by 2 and close the bracket, plus the next one, which is 1 times 2, close the bracket, and plus the last one, which is 0 times 2 and close the bracket. Then this last one, the most you put a power of 0 to it, the next one power of 1, the next one power of 2, up to the last one. In this case we have a power of 4. After this, you now come and take your calculator and say 2 raised to the power 4, meaning 2 times 2 times 2 times 2 up to 4. It will give you exactly this 16, and you see I'm multiplying it by the 1. And here the second one, I have 2 raised to the power 3. Do it with your calculator. 2 raised to the power 3 should give you 8. 2 times 2 times 2, multiplied by 1 and keep it like this. 2 raised to the power 2, which is 4, multiplied by 0. 2 raised to the power 1 multiplied by 1, and finally 2 raised to the power 0. We know any 2 raised to the power 0 is 1, then multiplied by the 0. Now, if I come back to this first bracket, I have 1 times 16. It will give you exactly this 16. The next one, 1 times 8, it will give you this 8. The next one, 0 times 4. We know 0 times anything is 0. We have 0 here. The next one, 1 times 2 will give us 2. And the last one, 0 times 1, which is also a 0. Now, let us add these ones. 16 plus 8, it will give us 24, plus these 2, it will give us 26, base 10. Then I do the same thing for the second number, which is this 1100011 base 2, and I'm asked to change it into base 10. What I will do is I'll take the first one multiplied by 2, second by 2, 0 by 2, the next 0 by 2, the next 0 by 2, then 1 by 2, the last one by 2. As usual, the last one here by our right hand side, the 2, we put a power of 0 to it. The next one should have power of 1, the next one should have power of 2, power of 3. In this case we have up to power of 7. And for you to get your answers, use your calculator. Start by this one, 2 raised to the power 6, 2 times 2 times 2 times 2 up to 6, it will give you 64. Here 2 raised to the power 5 will give you 32. Here 2 raised to the power 4 will give you 16. Here 2 raised to the power 3 will give you 8. 2 raised to the power 2 should give you 4. 2 raised to the power 1 should give you 2. And finally 2 raised to the power 0. Any 2 raised to the power 0 is 1. We have 1 here. Multiply 1 times 64. It will give you 64. 1 times 32. It will give you 32. 0 times 16. 0. 0 times 8. 0. 0 times 4. 0. 1 times 2. 0. Then 1 times 1. 1. So if you add this, your 64 to 32, it will give you 96. And if you add that 92 to this 2, it will give you 98. And you add it to this one, it will finally give you 99 in base 10. So now we are going to look at how to convert from base 8, which is a octal, from decimal, which is base 10, into base 8, which is an octal number. I have shown you how we can convert from base 10 to base 2 by successive division with what? 2, which is the base we are converting to. In the same manner, if you want to convert from base 10 to base 2, all you need to do is to do continuous division by 8. and at each step you keep the remainder you get, just as we did under the conversion to binary. Let us take a typical example here. Here we are given 75 base 10, 123 base 10, and 241 base 10, and we are asked to change them into base 8. Now I'll start with this 75. I'll divide it by 8. Take your calculator and say 75 divided by 8. If you do it, it will give you 9 point something. So what we are concerned with is this 9, the whole number, put it here. So if you want to get the remainder, all you need to do is to say 9 times 8. If you do 9 times 8, it will give you definitely 72. So if you take 72 out of this 75, you will be left with 3. That's your remainder. Now you see this 9 divided by 8, of course we'll get only 1 8. Taking 8 out of this, it will leave you with the remainder of 1. Then the 1 divided by 8, we know 8 cannot enter, we put 0 here, but the remainder of the 1 itself, we put it here. As usual, we arrange them from the bottom to the top. Therefore I have 1 1 8, oh sorry, 3. Therefore my 75 base 10 is equivalent to 113 base 8. Second example is 2123, and we are asked to change it to base 8. You first of all say 123 divided by 8, it will give you 15 point something. Use your calculator, you get that. So if you want to know the remainder now, what you will do is to say 15 times 8 will give you 120. If you take 120 out of this 123, it will leave you with 3, which is your remainder. Now you say 15 divided by 8, and if you do that, we'll have only 1 8 here. And if you take 8 out of this 15, you have a remainder of 7. Then you now say 1 divided by 8, of course, and 8 cannot enter 1, you leave it here, 0 here, and the remainder should be the 1 itself. Then arranging from bottom to top, I have 173 base 8 equivalent to 123 base 10. The last one, I'm given 241 base 10. I'm asked to change it to base 8. So what I will do is to say 241 divided by 8. Take your calculator and do it. 241 divided by 8, it will give you 30 point something. Now if you want to know what is the remainder, all you need to do is to say 30 times 8. Doing that will give you exactly 240. So if we take 240 out of this number, we will be left with only 1 as the remainder. Then we'll say this 30 divided by 8, it will enter 3 times 3 point something if you use calculator. Now just say 3 times 8, it will give you 24. If you take 24 out of 30, the remainder should be 6. Now this 3 divided by 8, we know 8 cannot enter 3. Therefore our answer should be 0, but the 3 itself is our remainder. And if you combine them from bottom to the top, you have 361 base 8, which is equivalent to 241 base 10. Now the next thing is the conversion from base 8 to base 10. And if you want to do that, just follow the example we have given above for converting base 2 to base 10. Here we multiplied each bit by 2, then add powers to the 2's. But here, since we are under base 8, we multiply each of the bits given in the octal number, we multiply it by powers of 8 with respect to the position. The rightmost will carry power of 0, and you continuously increase towards the left, and then you add everything to give you your answer. Let us take these ones as our examples. We are given 1160 base 8 and 2415 base 8, and we are asked to change them into base 10 numbers. And how do we do that? If we want to do that, we arrange them as we mentioned. Okay, as we are saying, let us take 1160 base 8 and try to change it into base 10 in this format. As I told you, we have used the tabular method above to change base 8 to base n to base 10, but here we are using a different method. Take this one, the first one, put it here, multiplied by 8. Take the next one here and multiply it by 8. Then take the next number, which is 6, multiplied by 8, and take the last number, which is 0, multiplied by 8. I'm sorry, here is supposed to be 8, not 2. So now you start by saying this 8 raised to power 3 means 8 times 8 times 8. If you use your calculator, it will give you exactly 512. The next one, 8 raised to power 2, 8 times 8, it will give you 64. The next one, 8 raised to power 1, will give you 8, and 8 raised to power 0 will give you 1, because any 8 raised to power 0 is supposed to be 1. Now, 1 times 512 will give you 512, 1 times 64 will give you 64, and 6 times 8 will give you 48, and 0 times 1 will give you 0. So add 512 to 64 to 48 to 0, you get 624 base 10, which is equivalent to 1160 base 8. The second example here is 2415, excuse me. We arrange them as usual. The first one, this is it, 2 multiplied by 8. The next one, 4 multiplied by 8. The next one, 1 multiplied by 8. And finally 5 multiply it by 8. And of course, sorry, this base is not supposed to be 2, but it's supposed to be 8. We are in base 8. Now, as usual, I'll come and say 8 raised to power 3, which will give us 512. 8 raised to power 2, which will give us 64. 8 raised to power 1, which will give us 8. And finally, this 8 raised to power 0, which will give us 1. You know, anything raised to power 0 is 1. Now, multiply 2 by 512, add it to 4 times 64, add it to 1 times 8, and add it to 5 times 1. If you do that correctly, to give you 1293 in base 10. So the next thing now is how to convert from decimal, which is base 10, to hexadecimal, which is base 16. As we did under binary and octal, all we need to do is to continuously divide the base 10 number given to us by 16, and in each step we keep our remainder, and after that we arrange the remainders from the bottom to the top to give us our equivalent hexadecimal result. And for us to illustrate this, let us use these numbers: 175 base 10, 523 base 10, and 2321 base 10. Let me start with the first one, which is 175. I will say this 175 divided by 16. If you see 175 divided by 16, it will give you 10 point something. Do it with your calculator. It will give you 10 point something. And if it give you that 10 point something, let me show you what I'm saying. Let's use our calculator here to show us that. Let me say 175 divided by 16. If you do this, it will give you 10.9 something. My concern is not this point something, is the 10. And if you can remember, in hexadecimal, our 10 is equivalent to what? To A. So I'll put my A here. Now, in order to know the remainder, all I need to do is to say this 10 times 16. If you say 10 times 16, 10 times 16, it will give you 160. So it means my remainder is 175 minus 160, which will give us exactly 15. So the remainder is 15. You can see here I put F because F is equivalent to 15. The next thing I'll now say A, which is 10 divided by 16. We know 16 cannot enter 10. Therefore, our answer is 0 and the remainder is the A itself. So my final result should be this. I'll combine the A and the F, starting from the A up to F. So my 175 base 10 is equivalent to AF base 16. Then let us go to the next one, which is 523, and we are asked to change it into hexadecimal. As I said, we will say 523 divided by 16. This is what it will give you, 32.6875. My concern is the whole number, which is 32. So I'll say my answer is 32. But you know, because of those points I have seen, definitely there must be a remainder. So how can I get the remainder? I'll now say this 32 times 16, it will give me 512. So out of 523, if you remove 512, it will give you exactly 11. Your remainder is 11. But you know, this 11 is equivalent to B in hexadecimal system, so you put B as your remainder. We now come to this 32 and say 32 divided by 16. That will give us 2 exactly without any remainder. Therefore 2 here, the remainder is 0. Now I'll say this 2 divided by 16, that is, how many times can we get 16 in 2? Of course it will not enter, we have 0, but the remainder is the 2 itself. Now my answer should be this, 20B, arranging from the bottom to the top. So 523 base 10 is equal to 20B base 16. Then finally we do the same thing for 2321, and we are asked to change it to base 16. What I should do is to take 2321 divided by 16. Doing that will give you 145 point something. As I said, my concern is the whole number. So I'll now say, let me put the 145 here. And to find the remainder, I'll say 145 times the divisor, which is 16, to give me 2320. Look at this. I have 2321. If you take 2320 out of it, the remainder will definitely be equal to 1. So look at my remainder. The next thing is to come to this number 145 and further divide it by 16 also, because we are changing to base 16. And if you do that, it will enter 9 point something times. But my concern should be what? This 9. We put it here. Now, in order to get the remainder, we'll say this 9 times 16, it will give us 144. You see, if you say 145 minus this 144, it will give you remainder of 1. Now, the next step is to say how many times can this 16 enter 9? Of course, it will enter 0 times, but the remainder is the 9 itself. So my answer should be this, starting from the 9, 1, 1. Therefore, I can say 2321 base 10 is equal to 911 base 16. The next thing is to see how we can convert from hexadecimal to decimal using a direct multiplication without using tables, because we have seen how we can do that using tables. So as we did under binary and octal, all you need to do is to continuously or multiply each bit of that your hexadecimal by 16, of that your hexadecimal by 16. And after doing that, you add them. The last one from the right should carry a power of 0, next one power of 1 up to the last one. And after doing that, you now come and add everything to obtain your result. Let's assume we are given 1 AC base 16 and 2 E5 base 16. Please note, here is not 8, is 16. And we are asked to change it into base 10. So what I will do is to see this 1 AC, my 1 multiplied by 16, plus my A multiplied by 16, plus my C multiplied by 16. So this is the last one. So the 16 should carry a power of 0, the next 16 should carry a power of 1, and the last one should carry a power of 2. Now I will say 16 raised to power 2, meaning 16 times 16. Take your calculator, let me show you. 16 times 16, it will give us 256. Look at it here. And then 16 raised to power 1 is 16 multiplied by the A, and anything raised to power 0 should give us 1 multiplied by C. Now if you say 1 times 256 is exactly 256, and if you say A times 16, we know A is equal to 10. 10 times 16, it will give us exactly 160. And here if you say C times 1, my C is 12. 12 times 1 should give me 12. So let's say 256 plus 160 plus 12, it will give you exactly 428 base 10. The second example is 2E5, and I'm asked to change it to decimal. I'll say 2 times 16 plus E times 16 plus 5 times 16. This is the last 16, it should carry a power of 0. The next one should carry a power of 1, and the last one should carry a power of 2. 16 square means 16 times 16 should give us 256 multiplied by the 2, and 60 raised to power 1 should be 16 times E, and 60 raised to power 0 should be 1 times 5. So 2 times 256 will give me 512, and this E, if you can remember, is 14. 14 times 16 will give me 224, and here 5 times 1 should give me 5. So let's add everything here. 512 plus 224 plus 5, I will get 741 base 10. So we go to the conversion from binary to octal. If you want to change from base 2 to base 8 directly, how do you do? These are the steps. Number 1, you split the number into 3 bits. The binary number given to you, try to split it into 3 bits, but you should start from the right hand side. And if you reach the leftmost and you found that you don't have up to 3 bits, what you will do is to introduce zeros in front of them, and these zeros are called leading zeros. And after that, each of the 3 bits you group now, you convert them into decimal equivalents, and then you arrange them to give you your required octal number. To understand this, let us illustrate with 2 examples. Here we are given 110, 100, 101 base 2, and here we are given 100, 111, 0, 11, 11 base 2, and we are asked to change them into octal, which is base 8. So in order to do that, I will have something like this. If you take this number, I'll take this first 3 from the right, which will give me 101, and then I'll come and take the next 3, look at them, to give me 100 here, and finally I'll take the last 3, which is 110. So in this case, I have exactly 3 bits without any shortage. So all I will do is to convert this one into decimal equivalent, convert this one into decimal equivalent, and convert this one into decimal equivalent. So if you want to remember this, you know that this last bit, it is multiplied by 2 raised to power 0, and 2 raised to power 0 is 1. The next one should be multiplied by 2 raised to power 1. 2 raised to power 1 is 1, and this one is multiplied by 2 raised to power 2, and 2 raised to power 2 is 4. Good. So if you multiply this one by 4, it will give you 4. And if you multiply this one by 2, it will give you 2. Then 4 plus 2 should give you 6. But 0 times anything, you know, is 0. So that's why my decimal equivalent is equal to 6. The same thing, here should be multiplied by 1, this one should be multiplied by 2, and this one by 4. And you can see this is the only place I have 1. So if you say this one times 4, it should give you 4, because the remaining are zeros. Therefore, multiplying them by anything will give us zeros. The last one, if you look at this, I'm given 101. You know, this one is multiplied by 4 as I explained, and this one is multiplied by 1. Therefore, I have 4 plus 1, which will give me 5. So I will arrange 6, 4, and 8 to give me 6, 4, 8 base 6, 4, 5 base 8. Now let us take the second example. As usual, this one I will divide it into 3 bits starting from right. Can you see this is my first 3 bits which I have here? Then I'll come to the next 3 bits, which should be this ones, which is 101. You can see them here. Then my next 3 bits should be this, which is 011, as you can see here. But if you look at this, I am left with only 1 and 0. They are 2 bits, they are not up to 3 bits. So as I told you, I should introduce this 0, which I call a leading 0. In this case, I only need 1 because they are 2. So putting 1 0 should make them 3 bits. So follow the procedure I explained here. You know, this middle number is multiplied by 2 and it is the only one. 2 times 1 should give me this 2. And here, the last one multiplied by 1 to give me 1. The next one multiplied by 2 to give me 2. And you can see that we have 4. And if you come to this one, multiply this by 1 to give us 1. And the last one here multiplied by 4 to give us 4. So 1 plus this 4 should give me 5. But if you look at this, I have everything. This one multiplied by 4. The next one multiplied by 2. And this one multiplied by 1. So 4 plus 2 plus 1 should give me 7. If you arrange these numbers, it will give us 2, 3, 5, 7. As you can see here, 2, 3, 5, 7 base 8. Therefore, we change this number into an octal, which is base 8. So the next thing is to see how we can convert directly from binary to hexadecimal. That is from base 2 to base 16. As we did under base 8, we split the numbers into 3 bits. But for base 16, we'll do the same thing but not 3. This time around, we split them into 4, starting from the right. And if the leftmost does not have up to 4 bits, we introduce leading zeros as we did on the octal. And each 4 bit is now converted into decimal equivalent. And finally, we arrange everything to give us our result in hexadecimal. To understand this, let us illustrate using these 2 examples. Now, starting with the first one here, you can see if I arrange this one, they will give me 4. That is 0, 1, 0, 1, as you can see here. Then followed by these ones, they are also 4, which will give me 1, 0, 1, 0, as you can see here. So after taking this 4 times 2, I am left with only 1 bit. So since I need 4 bits, I will introduce 3 leading zeros, as you can see them in bold here. So after doing that, I'll come to this and say, okay, I want to change this one into a decimal equivalent. As I told you, this one is multiplied by 1, followed by multiplied by 2, this one multiplied by 4, and this one should be multiplied by 8. Had it been I have another one, it should be multiplied by 16. But looking at this, you know, it is only this last bit that is 1, the others are 0. Therefore, this 1 multiplied by 1 will give me exactly 1. And if you come to this one, the leftmost is multiplied by 8 to give me 8, and this one is multiplied by 2 to give us 2. So 8 plus 2 should give us 10, and you know 10 is equivalent to A in binary. Now, if you come to this one, the last one multiplied by 1 to give us 1, and this one, the middle one, is multiplied by 4 to give us 4. So 4 plus 1 should give me 5. So now, if you say 1A and 5, you arrange them like that, they will give you 1A5 in base 16. Our last example is to change this one into hexadecimal. As I said, we are going to group them into 4. Let me start from the right as usual. See, if I take the 4 bits from the right, they are what? 1, 1, 1, 1. Then after this 4, the next 4 should give me this. They are 1, 1, 1, 0. Look at them. And if you look at the remaining, they are 3, but I need 4. So I introduce a leading 0 in front of this one, as you can see it here in bold. So I'll start the conversion. You know, this one multiplied by 1, this one multiplied by 2, this one multiplied by 4, and the last one by 8. So you can see it is the position of 4 that I have 1. So that 4 multiplied by 1 should give me 4 here. But if you look at this, this is multiplied by 8 to give me 8. This is multiplied by 4 to give me 4. And this is multiplied by 2 to give me 4. Then 2, then I have 8 plus 4 plus 2. If you add them, they will give you 14. And 14 is equivalent to E in hexadecimal number system. But if you look at this one, all the 4 bits are 1. So I have 8 plus 4 plus 2 plus 16. Adding these 3 will give me 8 plus 4, 12. 12 plus 2, 14 plus 1, 15. And you know, 15 is equivalent to F in hexadecimal number system. So arranging these ones will give me 4EF base 16 as my answer. Well, ladies and gentlemen, this is the end of our second lecture, and as usual, I would like to conclude by advising you to please take your time in an exclusive, please very silent, watch and listen carefully, try to get the ideas. You can play it as many times as possible, and in case you still have problem, please do not hesitate to ask me as well. You can ask your friends, they can help you to get it